Hello, welcome back everyone. This is week number 12 and I'm going to deliver lecture number 21, Fundamental of Econometrics. So let me start. We were in chapter 4 of the Econometrics by Example by Dominique Gujarati. The chapter 4 we are discussing is entitled as Regression Diagnostic number 2, and then we are discussing the topic of heteroscedasticity. So before starting this week course material, let me quickly give you an overview of what we have covered in the previous week so that we link our previous learning with the learning of this lecture and we have a logical bridge between our learning in two different time periods. Previous week we were discussing heteroscedasticity. I introduced the concept of heteroscedasticity. We did discuss that when there is a problem of heteroscedasticity, then what are the consequences of heteroscedasticity. Then we saw an example. We also did discuss different detection methods of heteroscedasticity, namely the graphical method, the BP test, and the Y test. I will quickly give you an overview of one slide each on these topics, and then I will proceed to the new topic. So the concept of heteroscedasticity is straightforward. It says that there are a number of assumptions of the classical linear regression model or the ordinary least square method, and one of these major assumptions is that the variance term of the error term of the regression model should be homoscedastic or constant. Mathematically, we can say that variance of the error term given the explanatory variable should be equal to sigma square or a constant variance. Then we says that when this assumption of constant variance get violated or not satisfied, we say that the problem of heteroscedasticity arise, or we says that it's an issue of unequal variance, and this unequal variance is denoted by sigma square I. Then we says that what are the reasons for heteroscedasticity? So we said there are many reasons for heteroscedasticity, like we can think of error learning data that's model like, or if it's of nature of error learning model, then we may think that there is a problem of heteroscedasticity. We did discuss that what is made by error learning model, so I don't think we need to repeat it here again. For detail, you can watch the previous lecture. We also talked about that when we mix different observations that are measured in different scale, that can also cause the problem of heteroscedasticity. And we did talked about mixing high income household with low income household. Again, the example has been discussed in detail in the previous lecture. We also talked about when there is an improvement of data collection technique over a period of time that may cause the problem of heteroscedasticity. We did discuss a case of two Pakistani bank as an example. Then we also talked about another reasons of heteroscedasticity being the presence of outliers in our data, and then specification bias and incorrect transformation of the data were the two other causes that may be possibly resulting in heteroscedasticity. All these reasons were discussed in detail in the previous lecture, so if you can't recall or if you can't link, I would strongly advise you to switch back to the previous lecture and then move with this video. The consequences of heteroscedasticity. So once we know what is heteroscedasticity, when we know why it happens, then we should also know what happens to the OLS estimators if there is a problem of heteroscedasticity. So in simple words, this means that although the OLS estimators are still unbiased and consistent, which refers that when we calculate their value or estimate their value, the true values on average are equal to the population parameter value, or consistency refers to when the sample size is increased to infinity, the true value converts to population value. But the estimators are less efficient or they are not best, which means that their standard error are not minimum. So when we can't have the minimum standard error, we can't trust the t or f statistic value because these are calculated using the standard error of the coefficient. So as a result, we say that the first major consequence of heteroscedasticity is that the OLS estimators are not best linear unbiased estimator, or they are not blue. They are just simply blue or linear unbiased estimator. Their variance is no more minimum, so they are not best. So when there is a problem of heteroscedasticity, we use a different method of estimation, which we call weighted least square method. Today we are going to talk about that. Finally, then we also did discuss previously that how we can detect heteroscedasticity, and we saw how we can do that in EVIEWS. So I will quickly tell you that in general we have a number of tests for in EVIEWS that can be used to detect the problem of heteroscedasticity in your data. If you recall our previous discussion on the topic of multicollinearity, we can recall that multicollinearity do not have a proper test. However, for heteroscedasticity, there are a number of statistical tests that can be used, and through that we can identify if there is a problem of heteroscedasticity. So the test which we, or the processes which we discussed previously were listed below. The first one was graphical method. In graphical method, we saw two approaches. The one was in which we saw the histogram of the square of the residual, and the second one was having a graph of residual square against the predicted value of the dependent variable, and we saw if this graph present a pattern, we can be suspect that there is a possibly problem of heteroscedasticity in our data. Then we saw two tests, a brush and pigeon test, and the second one was white test. These were the two statistical tests, and that were also we applied in EVIEWS and saw how we can detect heteroscedasticity using these tests. Besides that, there were some other tests which are also briefly discussed and shown on EVIEWS, that how these tests can be applied, and accordingly we can check for heteroscedasticity in our data. So that was week number 11. So now we are going to talk about the contents of week number 12, and this week two lectures are mainly focused on the remedial measures of the heteroscedasticity. So you can think of heteroscedasticity a problem in our data that having a consequences on the standard error or the variances of the population of the estimated parameters, and we have to fix that problem. So in this week we are going to see how can we fix this problem. So let's start with the background of remedial measure for heteroscedasticity. As I told you a while ago, again refresh your memories that when we apply OLS method, presence of heteroscedasticity, the coefficient we get are unbiased, efficient, but not best. So their variance is the problem. The coefficient have no issue, the variance of the coefficient have issue, because the coefficient are unbiased. So we in principle are getting the value of the population parameters in which we are interested, but their variance is not minimum. So the value can be obtained correctly, but we can't check it and we can't trust the results of the statistical test. So the issue is with the variances. So what we can do is that we can find a remedial measure for heteroscedasticity before we trust our OLS results. So we got the beta values, which is representing the value of the population parameter. But the problem is that we cannot trust it, that whether these are statistically significant at 1% or 5% or 10%. Why? Because the variance which is used for testing these hypotheses are not the minimum, or these are not the true variances. So in principle the beta values are okay, but their variances are not, and because of that we cannot trust our results of the OLS estimator. So to fix the problem, the big challenge which we are facing is that we do not know the true heteroscedastic variance, or in other words, we know that the variance are not constant, but we don't know if it's not constant, what are the values which are not constant. So the variance is absent. If the variance is unknown, it becomes difficult to fix the problem. What should we do? There are a number of ways through which we try to solve the problem of heteroscedasticity. So despite the fact that we don't have the true heteroscedastic variance available to us, there are a number of ways through which we can fix this problem. So we are going to discuss that. So moving toward the remedial measures for heteroscedasticity, there are different methods, and we can say that we can group these methods into two major groups. So the first group of method is under the case when we know the heteroscedastic variance, and then this method can be applied. And then the second group of methods are under the heading of the case when the heteroscedastic variance is unknown. So you can say that the remedial measures which are available can be grouped under two headings. The first one is the case when you have the heteroscedastic variance given, or if it's known, then you apply that method. And in the second case, when you don't know the heteroscedastic variance, so then you need a different method, and that method is placed in the second group. So let me explain it one by one, starting with the case when we have the heteroscedastic variance known. So when the heteroscedastic variance is known, all we have to do is that we transform the data in such a way that we can obtain the blue estimator, and hence our problem is solved. If our coefficient which we estimated were already linear, they were unbiased, and all we needed to do were to calculate or to ensure that we get the minimum variances. So if we somehow transform our data in a way that it ensures the minimum variance, our problem is solved. So how we do that? In principle, this process is called weighted least square method. So we already studied what is ordinary least square method. Now this is called weighted least square method. So you assign some weight and then you apply least square method. That's why it's called weighted least square method. Let me explain that method on the next slide. So weighted least square method is a procedure that we can apply when the variance or the heteroscedastic variance is known. Then we can apply weighted least square method to solve the problem of heteroscedasticity and ensure the blue estimator from our estimation procedure. So in this procedure is very simple as far as the understanding is concerned. All we have to do, since we know the variance, so we divide each observation with the heteroscedastic standard deviation or the variance sigma I, and then once these observation is divided by the weighted sigma I, this kind of assign weight to each observation. So once you have an observation, you divide it with the respective sigma I. That value get discounted as per the value of sigma I. So if an observation is divided by a small sigma I, it is discounted at a lower value, or because you are dividing some value with a lower value. And if you are dividing an observation with a larger sigma I value, so that value will become smaller, so that's discounted at a more heavily. So in another word, weighted least square method is based on simple logic that you know the heteroscedastic variance. You take that heteroscedastic variance and you start dividing each observation with that heteroscedastic variance. So once you do that procedure, you get a transformed data, and that transformed data is a kind of resulting a homoscedastic observation, because the heteroscedastic data is weighted based on the heteroscedastic variance, and thus it converts it to a homoscedastic observations. And these homoscedastic observations can be then used by you can say that you can apply OLS method to this transformed data, and you can obtain the OLS estimators, and we call these the estimator we get, or the parameters we estimate through this procedure having the property of blue. Or in other words, you transform the heteroscedastic data first to homoscedastic data, and then you apply your LS method and ensure the blue estimator. So this procedure is called weighted least square method. Let me revise it again in more simple words. We said that weighted least square method is a method that is applied to fix the problem of heteroscedasticity when we know the variance, the heteroscedastic variance is known. This procedure works as follows. First, we get the heteroscedastic variance, then we divide each observation of the data with the respective heteroscedastic variance. This process transforms the heteroscedastic data to homoscedastic data, and then we apply the ordinary least square method, and that process, these 2-3 steps ensure that the estimated parameters which we get are blue. So that's the weighted least square method. Now the method itself is very good. It sounds really good, but the problem is that we don't know the true variance. It's really known, so the problem is still there. So as the method may sound great in theory, but it is not practical because the variance is not known. So if the variance is not known, you can't apply it. So technically, there is a procedure, theoretically, there is a procedure available that could be used to fix the problem of heteroscedasticity by weighting the observations and then applying OLS and ensuring the blue estimators. However, that method cannot be used because we don't know the variance values. So what can we do then? So there is a second group which we call the methods that could be placed under the heading of the heteroscedastic variance unknown, or the case when the heteroscedastic variance is unknown. So what are these methods? So if we don't know if there is a variance, heteroscedastic variance, what can we do? So we make educated guesses about the variance and we transform our data accordingly to remove the heteroscedasticity. So let me rephrase the things. If the variance is known, so we apply weighted least square method that ensures the blue estimators. However, we don't know the variance. So in principle, although there is a theoretical method of weighted least square, we cannot apply it. So what could we do? We think of cases where the variance is unknown. So variance is unknown, okay. So what can we do? We make some guesses that, okay, variance is unknown, but it could be of this form or of this form. And then we use that unknown heteroscedastic variance, which we guess, and we use that to transform our data and remove the heteroscedasticity. So that's the simple way of understanding it. So all we have to do is that we find the unknown heteroscedastic variance. We don't find it, we guess them, and then we use that guesses value, that guessed value, for transforming our data and then accordingly removing the heteroscedasticity. So what could be the possible guesses which we can use? You can think of number of ways of doing it. So there are a number of possibilities through which you can make your guess and you can start. The first one you can think of, that we think that the true variance is proportional to one of the regressor or X variable. So you can think of one possibility that the variance is proportional to the variable, explanatory variable. So all we do is we take one of the explanatory variable, we divide the entire model, that is the Y variable, and each X variable with that X, and then we run the model and we see if the heteroscedasticity is removed. So that's one way of applying or remedial measure for having heteroscedasticity removed from the data. So let me, this may sound a little bit problematic for you. So let me try to explain it through writing some equation, and maybe that help. For example, I have this model y is equal to function of, I would not write the entire equation because it becomes difficult. So let's say I have this 3 variables So I have a dependent variable and I have 3 explanatory variables. Now this is our model, and we are having a problem of heteroscedasticity, and we do not know the heteroscedastic variance. So we want to apply this way of solving the problem. So all we have to do is, we are suspecting that this x1 is proportional to the variance. So what I do, I will take this x1, I will divide this y1 with this x1, I will divide this x1 with this x12, I will divide this x2 with this x12, and I will divide this x3 with this x1 again as well. And then I will use these new variable, which I can name as y steric, for example, and then this x1 steric, x2 steric, and x3 steric, and I run the model. Because the x sterics are the transformed variable, and we believe that this transformation has removed the heteroscedasticity. Now yes, there may be a question that, did this transformation ensure the removal of heteroscedasticity? That's still a question mark. We're going to talk about it shortly, but let me show you some more methods as well. So that was one possibility of number of ways. One possibility is that the error variance is proportional to one of the explanatory variables. So I can think of x1. Someone may ask the question, why not x2 or why not x3? Yes, that's a very valid point. We can try x2 and x3 as well, because we are in a way guessing we are guessing that the true variance is proportional to one of the regressor, not x1, just one of the regressor. So we can try with any of these. Now this procedure by itself raises a lot of question marks. I will be answer that in next few minutes, but first I want to mention some more methods as well. So the second method is that the true variance is being proportional to the square of the one regressor. So, well, it may be possible that instead of the original regressor, we use the square of the regressor. Let's say dividing y by the x1 square, and similarly x1 square and x1 square and x1 square, and then use this model, this transformation. And then, as I said, we are guessing. So it's a guess process. We can guess that we can use the x variable, we can use the square of the x, and suspecting that these are proportional to the variance, the true error variance. So these were the two possibilities. And you can think of a third possibility, that the error term being proportional to the estimated value of the dependent variable. So instead of using the explanatory variable, I use the dependent variable forecasted value. So how this works? So first I will take the model, I estimate it. I found that there is a problem of heteroscedasticity. Okay, so what I do, I forecast the dependent variable. I take that value, I divide each variable of the model with this forecasted value of yi. So this y is divided by yi forecasted. Similarly, x1 divided by yi, x2 divided by yi, and x3 divided by yi forecasted values. And then I use that transform data to estimate that model again and check if there is still a problem of heteroscedasticity. So that's the third way of doing it. Then the fourth way is, instead of using the x variable, I use the log of dependent variable. Sometime taking the log may also solve the problem of heteroscedasticity. So instead of using the regressing the y variable on the x variables, I think of taking the log of y and then using that as a dependent variable. Finally, I can think of using a double log model instead of the normal log model. That may also sometime work. So let me give you the entire picture. We said that the remedial measure for heteroscedasticity could be listed in two headings. The first one is the case when the heteroscedasticity remedial measure we use when we know the heteroscedastic variance. In that case, we use weighted least square method, and that method was a straightforward method that you know the heteroscedastic variance. You take that variance, you divide each observation with the respective heteroscedastic variance and then transform the original data to homoscedastic data and then or homoscedastic variance, and then you apply your OLS method and get the blue estimators. But the problem with that procedure was that we don't know the heteroscedastic variance, so that method may not be used. Then we says that there is a second group of methodology that could be used under the heading when the heteroscedastic variance is unknown. In that case, since we don't know the variance, so we make some guesses about the variance, that what could be the variance, and we use that guesses to transform our data and remove the heteroscedasticity. So 5 possible way of guessing has been listed on this slide. Some textbook use more than 5 methods. I just use these 5 believing that at this level these 5 could be effectively used to remove the problem of heteroscedasticity. So we guess that whether one of the explanatory variable is proportional to the error variance. So we use that particular regressor as a way of weighting our observation and then transforming our data and then applying ordinary least square method. Or you may think of applying the squared of the residue, the squared of the explanatory variable for the transformation, or using the forecasted or predicted value of the dependent variable, or using the log of the dependent variable instead of the original variable, or using the double log model. So this problem, this particular remedial measure may solve the problem of heteroscedasticity. So now let me highlight few things. This is very important point. Irrespective of which method we pick after the transformation and after re-estimating the model, we need to check again if the problem of heteroscedasticity has been solved and our data is homoscedastic now. So what I am saying in plain simple words, it means that once you apply one of the transformation method, the 5-1 which I show you on the previous slide, these 5 methods 1 to 5, if you apply one of these to your data, you transform your data, you re-estimate the model, you shouldn't be sure trusting your result that your data is now homoscedastic until and unless you reapply White or BP test and make sure that now your data is homoscedastic. So first you fix the problem. Since the fixing is based on guesswork, so you shouldn't be sure that the problem is solved automatically. You have to reapply the test and have to be sure that the problem of heteroscedasticity has been solved. So the other things which I want to highlight, that there are several practical problems in the application of this guessing procedure. So let me highlight few. Some of the questions should be there in your mind as well while watching and understanding these concepts. So the first logical question is that there are several variables, explanatory variables in our data. So if I suspect that one of the explanatory variable is proportional to the heteroscedastic or homoscedastic variant, how can I be sure that which one explanatory variable have link with the variance term? Which, or in simple word, which variable should I use for transformation, if I put it in more simple words? Yes, as I use x1, but we can also think of using x2 and x3 as well. So that's one of the practical problem you face when you apply this method. Yes, this is a problem with this method. Secondly, this is the answer to the first point as well, and this is also a built-in problem in this procedure as well, that this is a trial and error procedure and it needs a lot of time. So it's not like you apply the first approach of fixture and it will solve your problem. It's quite possible you apply the first procedure you guess that the one-off explanatory variable could solve your problem, so you pick that variable and you try the transformation, but when you apply the test your data is still heteroscedastic, so you have to pick another and then you try again. So it's a trial and error procedure because it's a guesswork, so it's not necessary that your first guess solve your problem, so you have to keep on trying until you solve the problem. So that's why we call it's a trial and error procedure, and it need a lot of time. And then we say sometimes some data variables have zero values. So if you use that for transformation, so you are dividing in observation with a zero, and obviously it will be undefined, so that cause a problem. That's a problematic. So that's one of the problem with applying these methods when the heteroscedastic variance is unknown. Then this should be noted as well that all the transformation method are ad hoc method. It's not a kind of a standard procedure. It's just an ad hoc method that somehow solve the problem of heteroscedasticity. So you should keep that in mind as well. But this is an important point that there is not much we can do about heteroscedasticity. All we have to do is we try with some guesswork to fix the variance, because at the end we don't know what is the homoscedastic variance. So we do some guesswork, and through that we try to solve the problem of heteroscedasticity. So to sum it up, we said that there are number of ways through which we can solve the problem of heteroscedasticity. We can divide that remedial measure into main heading. One, the case when the heteroscedastic variance is a known, and the second when the heteroscedastic variance is unknown. In known variance case, we use weighted least square method using the known variance. However, it's not practical because we in practice really know the true variance value. Then the second method, the second group of methods, which is under the heading of heteroscedastic variance unknown, there are 5 ways, possible ways, which I mentioned. There are more than 5, but I just mentioned 5 as per our the textbook we are following. So we use these 5 ways or guess through which we try to know or try to guess the relation between the data we have and the heteroscedastic variance, and we try to transform our data using that guess relation, and through that we try to solve the problem of heteroscedasticity. However, we do mention that because of this transformation, although the problem of heteroscedasticity may be addressed up to some extent, but that's the maximum we can do. And all these transformation methods are ad hoc methods. They are time consuming, they are trial and error based methods, and sometimes it may take a longer time because we don't know exactly which particular explanatory variable, for example, we should use for transformation, or sometimes it may create a problem if we have some zero values and we use it for transformation. The observation may have a problem. So these were few issues and ways through which we can solve the problem of heteroscedasticity. Despite all these facts, we can hope that the guess which we use turns out to be reasonably good and it solved the problem of heteroscedasticity. Obviously, it was all hardcore theory, and it wouldn't be sufficient to understand these whole concepts and grasp the ideas. So it's a very good idea. Now it's a good time to use some real world data and see the problem of heteroscedasticity and then fixing this problem. So now what we are going to do is that I'm going to apply some of these transformational remedial measures for heteroscedasticity in the mileage data, which we discussed earlier, and using EVIEWS, the software which we are using extensively in this video series. So let me start. I'm going to do some practical tasks in EVIEWS, and the procedure will be the same again. I will be telling you what to do. Then I will be requesting you to pause the video and apply the EVIEWS tasks in your own by yourself. Take the output and then match the output and then look into the discussion part. So what I'm going to do is I'm going to use that same heteroscedastic data we used last time, and let me refresh your memories with that data. This data has the following list of variables. We have the mileage per gallon, miles per gallon, average miles per gallon as a dependent variable, which is represented by mpg, and then there was a second variable hp, which was for engine horsepower. Then there was SP variable, which was top speed miles per hour, and then there was a third variable, explanatory variable, which was WT, that was vehicle weights, and that was in pounds. And we already run a model in which we regress the average miles per gallon on HP, SP, and WT, the three explanatory variables, and we last time applied the statistical test for heteroscedasticity, and we were confirmed that there is a problem of heteroscedasticity in our data. So now we studied the remedial measure for heteroscedasticity. We are going to use this data and we are going to see that how we can solve or try to solve the problem of heteroscedasticity using the remedial measures which we discussed a while ago. So I'm going to apply all these remedial measures for this particular data. So let me start the task 12.2. 12.1 was the estimation of this model. 12.2 is now the remedial measure of the heteroscedasticity. So let me start remedial measure using estimated value of the dependent variable. So that's the first remedial measure. Now if you recall, if I go back to that slide, let me, as you can see we have 5 methods which could be used to fix the problem of heteroscedasticity. So I'm going to start with the third method, ignoring the first 2 methods, because it's not like I suspect directly that I should use the dependent variable. I'm doing that because I feel like that's the easy way to start with. Otherwise, if I start with the first one, so I have to try 3 times x1 dividing y by x1 dividing y by x2. If this doesn't solve the problem, then I try y with x3. If this doesn't solve the problem, then I have to try x1 square, then x2 square, then x3 square. And if it doesn't solve the problem, then I move to dependent variables. So what I want to do is first I want to try the last 3, and if it doesn't solve the problem, then I will move to the first or second. So let me start. The first task is 12.2. The task is that I'm going to apply the variance being proportional to the estimated value of the dependent variable. There's the method I want to apply. So for that, what I have to do is first I have to estimate the model, mileage per gallon regressed on SP, HP, WT, the top speed, the horsepower, and the weight of the vehicle, the 3 explanatory variable. I estimate these model, and then I have to think that that we can fix this problem of heteroscedasticity by dividing the data with the forecasted value of the dependent variable. So once I run this model, then I have to transform this data, because that's how we can solve the problem of heteroscedasticity. So for this transformation, I'm going to use the forecasted value of the dependent variable yi cap. So I'm going to use these values, and then I'm going to try to solve if the problem of I have to, once I transform the data, then I will see if the problem of heteroscedasticity has been solved through this transformation. So let me show you first how we can apply that through EVIEWS. So in EVIEWS, first of all, you have to estimate this model. Obviously, you need the importation of the data and then opening it as a group, and then you have to estimate this regression model. So once you estimate this model, how you can estimate this model, you know that already, so I don't need to tell. So the next step is that I need the forecasted value of the dependent variable. So for forecasted value of the dependent variable, once I estimate the model, in the result window, I will go to proceed, and then within proceed there is an option of forecast. When I click on that option, a new window, a pop-up window open, and in that pop-up window I need to give the forecasted variable value mileage per gallon mpg underscore forecasted. So I will generate a new forecasted variable for my model. So that would be the forecasted value of the dependent variable, and I will check all other boxes, uncheck other boxes because I don't need the output being shown on that checkbox. So I will just uncheck that for a while, for now, and then I will press OK. So once I press OK, what will happen? I will get the forecasted value of the dependent variable. Now I need the transformation of the original variable with the help of this forecasted value. So what I do, I need to generate following few new variables. The first variable I'm going to generate is y transformed. So I'm going to divide the dependent variable with the forecasted value of this dependent variable. So that will transform this variable to the a new variable which I'm calling y transformed. That should be equal to the original variable divided by the forecasted value of the original dependent variable. So that gives me y transformed, or I can call it y static, it's up to me. Secondly, I use the same variable and I divided this beta 1 with the transformed forecasted. Now what is beta 1? Beta 1 is the values of 1 1 1 1 for all observations. So it's like if I have 10 individual, or if I have 10 vehicle, let's say 1 2 3 till 10. So beta 1 assume that it has value 1 1 1 for all. So it's in principle it's 1. So when I want to transform beta 1, all I have to do is that I have to generate beta 1 transform or C transformed. I can call it C transformed, and I divide this beta 1 with the forecasted value of this MPG forecast. So y forecast, sorry, MPG forecast would be better. MPG forecast. So I divide it with this. So I get C transform is equal to 1 over MPG forecasted. Similarly, I divided SP with again MPG forecasted, then B3 with again MPG forecasted. So SP transform, SP MPG forecasted, and then HP transformed with HP slash MPG forecasted, and then WT divided by MPG forecasted to get WT transformed. So I got 5 new variables. All these variables being generated by dividing them with MPG forecasted. So once I have this new transformed variable, then I have to run this model. Y transformed being regressed on constant transformed, SP transformed, HP transformed, and WV transformed. So that's the procedure for applying this particular method. And once I do that, then there are some questions which I have to answer. First, I have to run the transformed model. Then I will apply again BP and Y test for heteroscedasticity, and I have to check if there is a problem of heteroscedasticity in my data. So in simple word, we discuss a number of remedial measures for addressing the problem of heteroscedasticity. So once I apply one of that fixture and I re-estimate a model, then I have to apply BP test and or Y test and check if the heteroscedasticity problem is still there. If the test confirm that there is still a problem of heteroscedasticity, I will apply one of the other method which I listed out of that 5 methods and see if the problem is still there or if it's solved. Or if I estimate this model, and if the test says that the transform model has no problem of heteroscedasticity, so we are good. If it's not the case, then I have to apply another remedial measure and then see again, repeat this process. So I will pause the video now. I will request you open your EVIEWS, download the data, and go ahead with the steps which is shown on this slide and do all this analysis, and then move forward with this video. Okay, so your time starts now. It shouldn't take you more than 5 minutes. Okay, I will close this video here, believing that you will try with this EVIEWS output. I'm going to discuss the output of this particular exercise in my next lecture, and we will continue this discussion from this point onward in our next lecture. Thanks for watching the video lecture. I hope you like the learning session. And if you like it, please do subscribe our channel. Looking forward joining with you people again for next lecture. Thank you.